Let's discuss programming languages. The goal of any programming language is really to make a computer do what we want it to do. We're going to use it to solve problems, implement algorithms, things like that. So ultimately, we have a target. We have an actual physical CPU that knows how to do things. We call the things that the CPU knows how to do the instruction set. Now, the instruction set of a CPU is binary codes that work with the CPU to tell it to manipulate internal circuits in such a way that it produces some predictable output. And the problem is those instruction sets are not very human readable. Uh, in order to successfully get a computer to do what we want, we need to issue a very precise set of instructions to it. So if, for example, we were thinking of a dog, we might have an instruction that set for that dog, which might include the command sit. Obviously, the dog would be very happy to comply. If we issue commands to a computer, we have to, again, remain within that instruction set of the computer. So if we had a command like move AX BX, the computer would again be happy. If we try to make the computer or the dog do something that's outside their instruction set, like if we issue the command move AX BX to the dog, it's not going to happen outside of the instruction set. Same way if we tell a computer to sit. So our computer programs must be written in such a way that they end up as a set of machine instructions for a target CPU. And there's lots of ways for that to happen. We want machine code. Ultimately, we need a executable set of instructions for a specific hardware CPU. And how we get there depends on what our need is. Generally, computer languages span a continuum from what we call low-level languages through to what we call high-level languages. And so depending on a lot of factors, like how much control you have over hardware and how much complexity there is to the language, how much it does for you, is where we would generally place these things on this continuum. At the lowest level, we have the assembly languages. Assembly languages are extremely high performance. It gives you direct maximum control over the machine, and they are target specific, meaning that if you write an assembly language for an x86 processor, you cannot simply port that over to an ARM processor or some other RISC processor. The instruction sets are different, and therefore the assembly languages are different. They're also not exactly human readable. They have weird codes that do include some sort of English language, like a move command. Obviously, moves things between memory locations, but but you are responsible for building all of the constructs. If you need to loop, you need to actually construct that looping out of a set of instructions in the assembly language. So they they are the go-to when you want to do something extremely precise, like an operating system kernel maybe, or a hardware driver. Uh, the next level up are what we would call the intermediate languages. These are languages like C, for example, and these begin to introduce a high level of abstraction. We can use constructs like for loops and arrays and things and not have to worry about directly manipulating memory and things like that. But we also retain a lot of direct control over the hardware. If we want to, we can get down pretty low in the control of the computer. As a result, these intermediate level languages tend to retain a lot of performance and yet are usable, are functional for humans to program in without too much difficulty. And then at the highest level, we have what most of us would program in nowadays, what we would consider to be current or modern languages. And these are share a lot of features with the intermediate languages. They are also high levels of abstraction. They're a little bit easier to read in some cases. They have a lot of built-in functionality, and they are also very. Some of them are very customized to specific tasks. like R, for example, is excellent for doing statistics. Um, some are very general, like Python or Java. The thing, the other advantage of some of these highest level languages are some of them are in fact somewhat target independent as opposed to the assembly languages. Something like Java with a virtual machine that can target a wide variety of processors and operating systems is an advantage to some of these. The disadvantage, of course, is sometimes you want more direct control over how your operation is being executed, and some of these languages kind of shield you from a lot of that control. Languages generally come in two forms, compiled or interpreted. So uh, the ultimate goal is they have to be converted into machine language, and the method by which they are converted is somewhat different in a compiled versus an interpreted model. In a compiled version, a source file, this is where you have written your code, solved your problem your way. Source codes have to run through a compiler, which is a piece of software that translates the source code language into some sort of machine executable code. The output is what we call an intermediate object code file. This object code is generally your programming logic converted into machine language, plus references to any sort of external resources that you may have used in your development. These would include standard library calls to, for example, write something to the screen or read something from a hard drive or something. These are built-in functionality that exists, and so they are not included in the object code directly. Instead, they're included as references. So in order to have something we can actually run, we have to link those external resources together using a program called a linker. And the output is an executable machine language file. We usually call them an executable file. And the nice thing about this process of compiling and linking is the executable machine language code is now ready to run independent of us doing these linking and compiling processes. So once we have an executable, we can just run it whenever. The opposite of that is the interpreted model, which is you start with the same source code, but instead of running it through a compiling and linking process that builds the entire executable, the interpreter, which is what runs the program for us, looks at it like line by line and determines a machine code equivalent for that line of code and executes it. So you never actually build an executable file in the end. You execute in place. And of course, there's advantages and disadvantages to both of these models. One thing we consider is what's done at build time. In other words, when we have an opportunity for the compiler and linker to optimize code and things is one of the advantages of the compiler model. The output is also faster because a lot of the slow work of figuring out what is this code supposed to be doing is done in the compiling stage. So the person building the application is the one that is spending the time with the analysis phase, and then the person using the program is just executing optimized code. Sometimes, or at least a lot of people nowadays, use this compiler linker model together in and editor, the source code editor as well, together in what we call an integrated development environment. A lot of people don't even know anymore that they are in fact using a compiler and a linker. They, in an IDE, will have a run button, for example, or a build button. And when they hit that, the IDE actually goes through a process of cleaning up your reference files, building the intermediate code, sending it to the linker, linking all of the things, and outputting an executable file. And in the case of a run button, then executing that executable file. It's very convenient. While some people prefer still to run individual compilers and linkers so that they have more control over the build process. So in an interpreter model, a lot of the stuff that can be done at build time in a compiler model, like optimizing code, in a compiler-based model, the compiler has an opportunity to look at broad sections of a source code and determine optimizations that could be useful, removing unused variables, expanding out loops and things in such ways that it produces highly optimized executable code. The interpreter generally doesn't have the ability to look too far ahead and figure out what is actually happening in the code. It really has a myopic view of only one or a few lines of code at a time. And so generally, compiled code runs faster than interpreted code. So what are some of the advantages and disadvantages of compiled and interpreted models? Well, the compiled model has highly optimized execution. The end result code runs very quickly. The syntax and semantic problems are found during build time generally. Uh, Interpreted code, the main advantage here is write once, run multiple, meaning that I can take, say, for example, a basic file and file in the language basic. If there's an interpreter that runs on my Windows program, if there's a one that runs on my Apple OS, if there's one that runs on my Linux OS, I could take the same basic source code file and I could run it on any of those platforms because it's up to the interpreter that's implemented on that platform to handle all of the conversation with the actual operating system and hardware. The other advantage on the interpreted programs is a quick development cycle. You don't have those, especially on larger projects, you don't have these large compile time sequences. You can just execute one little section of code and it only loads in those few lines and runs them, and you can quickly debug and diagnose some of your logic issues. What happens if we could come up with a hybrid or the best of both worlds? Well, this is sort of the Java model. Instead of compiling your code to final machine code that is specific to a real physical processor and operating system, Java compiles to this intermediate bytecode language. It's sort of like a machine instruction set for a virtual common processor. So Java compiles to this intermediate bytecode software, and that's been optimized. It has gained the optimization of the compiler, and then that code runs on what we call a virtual machine, and that virtual machine is like an interpreter that is going to be taking the bytecode and implementing it onto a specific target platform like a Linux virtual machine or a Windows virtual machine. When we talk about a computer language, what are we really talking about? Well, a programming language consists specifically of the reserved words, the syntax, and the semantics of a language. It's very similar to what we have for a spoken language. These are things like vocabulary, rules, and meaning. The reserved words are, in effect, the vocabulary of that programming language. These are the words that you're not allowed to change the meaning of in the programming language. So, for example, in a C programming language, you might have for as a reserved word, or while, things like that. Syntax is the order and structure of the written code. So, for example, the word order of building a for loop is different between different programming languages. The concept is the same, but the actual arrangement of symbols on the page is going to have meaning that is different between programming languages, and you have to get it correct syntax in order to be accepted by the language. And then semantics is the meaning of your code. Your code might be syntactically correct. You may have the symbols in the right order, but it may not do what you intended to do. You may be thinking it's going to loop 10 times and you've written it in such a way that it's going to loop infinitely. You've made a semantic mistake here. So if we were to use some English language examples of this, we might be able to write a sentence like, David eats the beans. This sentence has a subject, it has a verb, has an object, has a period, has capitalization. It meets all of what we would consider to be correct syntax for an English language sentence. we might rearrange the word order, and we can still identify eats as a verb, but beans David eats the now doesn't quite make sense syntactically. We're not sure the word order has caused problems. We can't identify a subject here anymore. So this sentence would have syntax problems. It also doesn't have a period at the end, so technically it's not a sentence. And we can take the same thing and reorder it again, and we can end up with a syntactically correct sentence like the beans eat David and have a semantic problem. What does this mean? We all kind of know that beans can't eat, so this might be a metaphor or something. But in a programming language, there are no metaphors, so meaning has to exist, and this is an example of a syntactically correct but semantically incorrect message. So how's that work in computer languages? Well, here's a few sample codes from different languages, and you'll see that they look different. They're all accomplishing actually the same thing here, which is determining whether an integer is even or odd. And I highlighted some of the words here that might be considered reserved words in those codes, and some of the things that aren't. And it's funny that, like, if you're a C programmer, you think of printf and scanf as so common to your functionality in your code. You probably have thought of almost of it as a reserved word, but it's not. It's actually an add-on to the code. The amount of stuff that's actually reserved in the language itself is actually pretty small, and you tend to use a lot of material from outside sources when you're building code. The other thing too is the syntax is different. For example, you'll notice in the C code, all the lines end with a semicolon. That's required. That's like punctuation. In Python, it's indentation that's significant instead of curly braces, for example. A different way of accomplishing the same thing, so syntactically they are different. No semicolons, indentation is meaningful. Meanwhile, in the C code, you could have written it all on one line. And assembly, as you see, completely different again. So if most of what we talk about or what we talk about as being in a computer language is fairly small, what actually is in that language? Well, you have the core language definition, which includes the keywords, the syntax, and the semantics of the language. That will give you the basic framework in which that's a bad word to use. The basic pieces that you need to use to write the solution. Along with that, you're generally going to use a set of tools. You're going to need a compiler. You're going to need an editor. You're going to need a debugger. You're going to need a lot of tools that go along with the language that allows you to actually turn it into functioning machine code. This is why I chose not to use the word framework just a few seconds ago. You will also need what are called frameworks in a lot of cases. These are large constructs of useful code that other people have optimized and written to take care of a lot of functionality that is common to computer programming tasks. An example might be, say, the .NET framework. This allows you to make a simple call to create a windowed environment. In the old days, we had to write in C code all these calls into the Windows operating system to individually create windows with frames, with close buttons, etc. This was often referred to as boilerplate code. Every single one of us that wrote Windows programs had to write this same exact code. And thankfully, as the tools evolved, a lot of these tasks became behind the scenes tasks built into usable frameworks. We also have external libraries. This is a call to a piece of code that somebody else has written and has already compiled into a runnable, executable piece. And so we might link to a library that does math for us and calculates some or generates, say, an SSL key or something. We may have libraries that we can just simply call and say, do this task for me and give me back the answer. So when you've built your core language source code and used these other pieces together, you can get an executable code. But there's really two more things we consider to be part of the language, which is a paradigm. Paradigm is a way in which we think about programming. Some languages are very specific on their paradigm, their model of how you program in that language. And then, of course, there's abstractions like how do you store your data? What data structures do you build? What algorithms do you implement? And some languages lend themselves to certain types of abstractions. So paradigm, if being one of these things that we talk about, is the approach to programming. There's lots of ways to think your way through a problem-solving situation, and in the world of programming, we generally have two ways to think about our programming approach. And some people stick very tightly to one of these two, and some people flow kind of back and forth between them. And and some people have very strong feelings as to which methods are better. So we can think of programs as being either in the imperative model or the functional model, or imperative paradigm or the functional paradigm. The imperative paradigm, we consider the program state to be sort of the dominant way of thinking of it. It's a big bag of information that we're going to modify and make changes to. So in the imperative model, you are free to modify system state whenever it's necessary for you to solve your problem. In the functional paradigm, we try to keep our hands off of the system state. We do everything through a predictable function call. If we want something to happen to the system state, we pass into the function some portion of information, and out of that function comes a modified answer, an answer we can then utilize. And those functions are repetitive and predictable, and they don't modify things that aren't within their little realm of control. Perhaps an analog that you might think of for this is in the imperative model. If I wanted to wash my car, I might go out in my driveway and get in there and start washing things. And it's all about changing the individual state of all pieces of this car as I go along. I'm thinking about the car and modifying its state of cleanliness. In the functional model, I would take the car to the car wash and I would drop it off at the back door of the car wash. I would get out of the car. I would walk to the front door of the car wash and my car would come out clean. I'm not the only thing that car wash building should do to my car is clean it. If I take my car back to that car wash, when I stick it in the end door, it's going to be dirty, and when it comes out the front door, it'll be clean every time. The other thing we have to think about in terms of paradigm are procedural versus object-oriented language. Uh, these four things can be combined in any way. So you can have imperative, procedural paradigm. You can have an imperative object-oriented paradigm. You can have a functional procedural or functional object-oriented. So they mix and match. The most common paradigm in use today probably is imperative object-oriented. The original programming languages tended to be imperative procedural. Um, Procedural programs are, again, a way of thinking about process first. You think about solving your problem by how am I going to go through the solution process, or how am I going to modify information? And so you think in terms of algorithms and processes and function calls and procedures. And then within that thinking of how you're going to be processing things, you then build data structures that you will use along the way to store the information during this procedural work. In an object-oriented model, you generally think of, well, what is the data that I'm going to need to manipulate? And then after you have a sort of a model of what information do you need to store in order to solve this problem, you then associate functions and abilities with that data. So you generally think, what are the things that might be done to this data? And those become procedures inside of these objects. So the end results are kind of the same. It's just which model works best with your version of problem solving. The other thing is when you pick a programming language, sometimes your target is important. Some languages are built in such a way that they have a lot of features that are useful for building out particular functionality. Like if we were building a machine controller, we might pick C. Why? Because we get that low-level access with some high-level constructs. If you're writing an OS kernel, for example, you might use assembly because you need it to be run extremely fast because it's called continuously from all sorts of programs running on the computer. Video game you might write in C++, mobile apps Java, business layers in Visual Basic. A lot of times you say the word Visual Basic and programmers cringe, but if you're in a business world and doing a lot of business processing, Visual Basic is widely used. Web apps might be, say, in Python. Web apps could be in a huge wide variety of things. And the other thing to consider are what resources are available to you. If you find a little niche programming language where only 7 of you in the world are using it, that may be super fun, but at the same time, when you get stuck, you only have 6 other people that you're going to be able to ask about. If you pick one of the mainstream languages like Java, for example, there's huge Java programmer communities available to help you. Same way with source code, access to the actual source code of the libraries and compilers that are written here in your language might be very useful. Documentation, third-party libraries, what tools are available? Are you stuck with a basic text editor and a basic command line compiler, or do you have rich IDEs that will help you produce code quickly? And platform access. Does your compiler exist for your target platform? If you have a language with no compiler to a target, then that language is not a good choice. So a final thought is that programming languages exist. There's a bunch of them nowadays. A lot of them are very general, like Java and C Sharp and C++, that can do wide varieties of things. And some are very targeted to specific tasks that they are fantastic at doing, like R, for example, for analyzing data. Um, so be flexible in your language choice and in your mindset. Uh, don't get sucked into the religious debates of which language is better than the other. They all have advantages, they all have disadvantages, and really the goal is to be productive. So find ones that work for you and make great things.